Hello and welcome to the fourth video in our series on the cash in advance model. In this video, we're gonna take a look at all that work we did deriving those first order conditions and see how we can use that to say more about the equilibrium of the model. The first thing is we can always interpret these conditions, but solving them is very hard. Part of it is because the solution is an infinite sequence of values and we won't be able to find them all. We actually only know the sequence of some variables, most of them because we know them from market clearing, two of them because we know them from the labor market problem. But by further examining the constraints and the first order condition, we can actually make some headway in saying more about the equilibrium of the model. So take, for example, the cash in advance constraint. If you replace for the equilibrium values of the variables, you can find out that actually it simplifies quite a bit because the value of b is 0, x is 0, b is 0, x is 0, and m is 1, you get a much simpler equation that's going to be relating the nominal, the value of the expenditure in consumption and the value of taxes or transfers. And so we know that this value of taxes or transfers is minus alpha from the government budget. And so this equation is going to give us a nice expression for how this real price, PT, depends on total consumption. It also tells us what's going to happen to transfers, to these real taxes, because once we know PT, we also know TT. So this expression is actually doing headway, in making headway, in terms of finding out the relationship between the different variables. We can do a similar exercise with the budget constraint. Here is the budget constraints once we have already implied all the equilibrium values. So we've already made it so that the wage is equal to z, m is equal to 1, this is m plus 1, that's going to be mt plus 1, that's going to be 1 as well. And so we've already replaced all of those. If we further replace from the government budget pt times tt by minus alpha, you can see that the alphas cancel and the 1s cancel as well. Then the p's are going to cancel as well, and we actually find consumption. This is what I meant by Walras's law. By imposing equilibrium conditions on all the other markets except for one, you actually find from your model that the final market clearing condition it's satisfied. In this case, it's the goods market clearing condition that's going to be saying CT it's equal to total output. Now, we can use the first order conditions to get an expression for labor. How are we going to do that? Let's focus on these three conditions because they actually tell a story about what the agents have to do in the model. And this is how we can use the math to better understand what's actually happening. We have the first order condition for consumption, for money, and for labor. How are these three linked? Well, working gives you resources. Those resources are valued at mu t. So working gives you pt times zt resources, and those resources, they go into the budget constraint. They are valued with mu t. That's going to be the multiplier of the budget constraint. But you cannot use those resources to consume right away because in order you consume before you got paid, you needed to consume out of your cash in hand. So you need to save these resources as money to spend in the future. So you need to work, that's going to cost you some utility. You get some resources which you value with mu. You take those resources and you save them as money. So you can take them as save them as money, and that money, which is a liquid asset, you can use in the next period to consume. That's going to be the value lambda t plus 1, mu t plus 1. But what is the actual value of this? Well, it's the fact that you can consume more in the future. The value of that additional consumption in the future is going to be given by u prime of consumption in the future. And that's how these three variables are linked through the restrictions of the model. When you work, you get some income, you want to use it to consume. In order to consume with that income, you have to save it. You save it, in the next period you can consume, and so the value of that income is linked to the value that you get out of relaxing your constraints in the next period, And that value is given by how much you get in terms of utility for the additional consumption. Let's see how that plays out. We start with our labor first order condition. We're gonna then replace mu t for the value of those resources. And that's gonna be lambda t plus 1 plus mu t plus 1 over 1 plus alpha. But then we wanna use this money for consumption. And so using the consumption first order condition, we know that lambda t plus mu t plus 1, it's u prime of ct plus 1 over pt plus 1. Let me just go back and you can see it here. Take this first condition, divide by pt, so you get u prime of ct over pt, but then you don't want lambda t and mu t, you want lambda t plus 1 and mu t plus 1. So you take all the condition and you shift it up one period into the future. So you get the ct plus 1 over pt plus 1, it's equal to lambda t plus 1 plus mu t plus 1. And that's exactly what we're doing here. Lambda t plus 1 plus mu t plus 1, you replace by u prime of ct plus 1 over pt plus 1. But now you can go one step further because you already had a relationship between pt and consumption. So you can use that to show that this is actually the growth rate of consumption here between pt and pt plus 1. It's ct plus 1 over ct. Just, I'm gonna go back for a second so that you can see it. That's coming from this expression. pt, it's negatively, it's inversely related to ct. So when you replace it, you get pt over pt plus 1, you get ct plus 1 over ct. You can do the steps on your own, but I just wanted you to see it right there. And this actually solves for the equilibrium. If we were able to solve this equation, because we know from the previous solution we did with the budget constraint that ct is equal to a function of n. And ct plus 1 is, of course, that same function in the future. So the only variable in this equation is the sequence of labor. So we have this, and this actually determines the equilibrium. This expression characterizes the equilibrium solution of the model. Of course, once we replace ct for its equivalent in terms of output. But we cannot solve it. We cannot solve it, and there are two reasons. One is the equation involves variables in different periods. We don't know what to do about that. The second one is we need a functional form for the utility of consumption and this utility of labor to actually be able to solve it by hand. Now, we won't do much about the second one, but we can definitely solve the first one. Before we do that, let me just notice that we also don't know Q and S. Now, what we can do is we can focus on the steady state solution of the model. And in these last couple of slides, that's what we're going to do. So the steady state is a special type of equilibrium where variables do not change across periods. So consumption has the same value for all periods, labor has the same value for all periods, and so on. This actually simplifies things quite a bit. Take, for example, the two first order conditions for nominal and real bonds. These are exactly the same first order conditions we had before. If you take out the time dimension because you're in a steady state and variables do not change, these conditions simplify quite a bit. Actually, you can see that the lambda plus mu cancels on both sides, and here the price cancels as well. So these two conditions in steady state actually solve for the prices. We now know what the price of the nominal bonds is, beta over 1 plus alpha, and the price of the real bonds, beta. If you see, that also gives you a relationship between the price of nominal bonds and the price of real bonds. Basically, S over 1 plus alpha, it's equal to Q. Now, at these prices, and this is important, consumers are indifferent between accumulating or not any type of assets. These conditions are actually non-arbitrage conditions. You can verify that. They are not arbitrage conditions. That means that they don't care. They don't care if they are saving in nominal bonds or in real bonds. And so because of this indifference, you can actually make it so that they are zero. Only when they are indifferent between all these different assets is the savings in the assets equal to zero, because that's when they don't want to do it. Okay, that's the only way you can get them all to agree that they don't want to save in either nominal or real bonds. If one of the two was better than the other, then you will have savings in one of them. Okay, so we can see the prices. What can we say about quantities? Oh, sorry, I forgot. But before that, uh, we can also relate these two prices to interest rates. Remember from Module 5, I'm sorry, remember from Module 5 that you can relate the price of zero coupon bonds to the nominal interest rate or the real interest rate, depending on whether they are nominal or real bonds. And so this gives you also an expression for the nominal interest rate being equal to 1 plus alpha over beta, and the real interest rate being equal to 1 over beta. Now, this is amazing because this already gives you the sense of what the Fisher equation is going to do. 1 plus r is equal to 1 over beta, so that means that 1 plus nominal r is 1 plus alpha times 1 plus r. Alpha is the growth rate of money, and here we're already seeing what's going to happen. Inflation in this model is going to be related to alpha. It's actually going to be given exactly by alpha. We're going to see that explicitly in the next video. Now, to close this video, let's go back to the expression we had that was determining the quantities of the model. This is the equilibrium condition that's going to relate labor to labor in the future or consumption, since they are all tied. But in a steady state, this term goes away. And not only this term goes away, you can also replace by market clearing. And so this is a condition that precisely characterizes the equilibrium just in terms of labor. Not only that, you know that one side of the condition is decreasing on labor and the other side is increasing. Why is that? Because the cost of working more is increasing the more you work. This side here is increasing. The more you work, the more consumption you get, and the less marginal utility that implies. So this side here is decreasing. So we can use this equation to figure out not only the equilibrium, but also some properties of it. Once we've solved this equation and we know n, then you can use n to get consumption to get prices, and also to get transfers. So that kind of solves all the quantities. How does that look? Well, here I'm graphing the left-hand side. That's going to be the just the marginal utility of additional labor through consumption, and the right-hand side is going to be the marginal disutility of labor. Then, of course, when they cross, that's going to be the steady state level of labor. So that will be how you solve it. In the next video, we're going to talk about the role of inflation in the model.